Hey, James. It feels like for a while there, quantum computing was just this magical answer to absolutely everything, right? Like it was going to solve world hunger and do my taxes instantly.
Right, Emma, exactly. And that's precisely the sentiment we're seeing shift quite dramatically, isn't it? The initial hype, you've hit it on the head, was about this universal problem solver. But what experts are really saying now is, well, it's a bit more nuanced than that, isn't it? It's not about replacing classical computing entirely, it's really about finding its specific place.
Oh, so like not every problem gets an exponential speed up then? Because that was the big selling point initially, like everything's going to be faster.
Precisely. The idea that quantum computers can just find all solutions at once by, leveraging superposition, it's a bit of a misunderstanding. While they can explore many possibilities, it's not an instant check for everything. And terms like quantum supremacy, which we now often refer to as quantum advantage, they really just demonstrated a theoretical point. It's not necessarily useful for everyday real-world applications just yet, you see.
Okay, so if it's not this universal magic bullet for everything, what is it really good for? Like, where does it shine, James?
Excellent question, Emma. It's increasingly viewed as a specialized accelerator, designed for what we call high-dimensional problems, where classical systems, they just really struggle. Think about, say, optimizing delivery routes, super complex financial calculations, or even simulating the behavior of large molecules for drug discovery, identifying compounds for undruggable proteins, that kind of thing. It's also big in cryptography and, speculatively, certain AI and machine learning algorithms. It's meant to address bottlenecks, not just, take over everything.
Oh, that makes sense. So it's like a really powerful, very specific tool in the toolkit, right? Not the entire toolkit itself. So classical computers aren't like suddenly broken then?
Absolutely not. Classical computers are, they're not broken at all. They're stable, predictable, brilliant for general purpose tasks like, what we're doing right now. The future, many experts believe, is a hybrid quantum classical approach. Quantum processors tackling those niche, incredibly intensive subproblems, and classical systems handling everything else. It's a collaborative model, leveraging the strengths of both, you see. It's all about problem fit, really, not just sheer scale.
That's super interesting, James. So we're talking about fit, not just how many qubits. But what's holding us back right now? Like, why isn't this hybrid future already, totally here?
Well, Emma, there are significant practical challenges, I'm afraid. First point, qubits are incredibly fragile, aren't they? Highly sensitive to environmental noise, prone to errors, which means they need extreme cooling and complex error correction. Current error rates are miles higher than classical computers. Then there's scalability. Achieving fault-tolerant quantum computers with the millions of qubits needed for practical applications, that's a monumental engineering challenge. And the software side is complex too, with a lack of mature tools and frameworks.
Wow, so it's not just like plug and play then. And so what we have now, like what do we even call these current systems?
Right, we're in what's called the noisy intermediate scale quantum, or NISQ era. These devices, they've got tens to hundreds of qubits, but they come with high error rates and limited scalability. They're not quite ready to revolutionize business operations, not yet anyway. The thing is, this discipline in thinking that we've been discussing, it's absolutely crucial. It's about not letting possibility turn into exaggeration, focusing on rigorous validation, and understanding where quantum computing truly belongs. It's a long game, this one.